Hey guys, today I'm going to be talking about the network flow problem, which is also known as like the max flow problem. And when we first see the problem, we're like, oh, this is so complicated and how are we going to solve it? But the algorithm turns out to be very simple. The Fulkerson algorithm can be actually just concluded with like 3 steps. So first, we're going to start with the initial flow at 0, so no flow goes over the entire graph. Nothing is carried from like the target to from source to the target node. And then while there's an augmenting path from source to thing, we're going to add this path flow to the flow, and then we're going to return the flow. But to decide whether there's an augmenting path from S to T, we're going to use something called residual graph to keep track of what we already like sent to the set of flow and what's already left, like what capacity is like still left from one node to another. So I'm pretty sure that you guys are already familiar with the residual graph that we learned in class, but I'll still show you what it looks like along the example I'm going to be introducing in the next slide. So here's what we were trying to solve. We want to do a max flow problem using this graph. And yeah, so let's start it. So this is the source node and this is the target node. We're trying to carry as much flow as possible from S to T. So here, 4, 4, 2, this is obviously an augmenting path. And to draw the residual graph, we're basically going to carry as much as we can, which is 2 in this case, because this is the minimum number. So if we carry 2 along this edge, we're going to have 4 minus 2 equals 2 capacity left from S to say like node 1. But at the same time, we can actually take 2 back from 1 and then, like take it back. So this we add this thing on the residual to the residual graph as like a way to remember how much we can take it back. Yeah, so this is like the first graph and here is the same. We do 2 and then back we have 2 again. I'm sorry, this number is like kind of like same everywhere, but it's not the same meaning. This 2 is the left capacity from on this edge and this 2 is what we can take back. Okay. So next route can be next augmenting path is like 3, 6, 6, and this 3 is all taken. So we just change it here. Sorry, this 2, like there's no capacitor left because, and this is 3, and this is 3, and we take it back. It's 3 again, and this is turned to 3, and then we're gonna take back also 3. Yeah. So, and the next step, let's try to find if there's another augmenting path. Obviously, we see there's still 2 left. So we can go this way, this way, this way, this way, and this way. So the min is 2. So we're gonna, take this to be 0. Like this is just eliminated, and this turns into 4. And here again, like this is 4, and this is eliminated. On this 3, it's not all using, but it doesn't matter. Like we don't have to use it all. Like as long as like 2 is like smaller than 3, we can use this. And 2 smaller than 3 here, 3 here. So I'm not gonna finish this graph, but that's like the last augmenting path. Like after we do this, we cannot, like we see that, like we cannot go from S to T anymore because all the edges that's next to S is pointing at S instead of pointing at some other node from S. Like it's incidented to S, not from S. And that's like we can't end to like the algorithm. And when we look at that new picture, that returns the flow. Like it's all constructed by the residual graph. Okay, thank you for listening. Have a good time.